Hi, there is a new tool called ChatGPT that is available right now where you can ask it a whole bunch of questions, and many students are using these to solve their homework problems, namely in programming. And that has some reasonable success, at least from what I've seen, where I plug in some of the questions that I asked on homework assignments for programming, and it gives me the correct answer, often better than student submissions, believe it or not. So what I thought would be interesting would be to look at a past theoretical computer science exam and see what actually happens. So let's get started. So here's the first question right here. It's a bunch of true and falses, and what I'm going to try to do is look at the feedback that ChatGPT gives and try to see whether or not it actually is correct. So I'm just going to do complete copying and pasting without any modification unless there's a reason to do this. So these are all true and falses, so I'm going to put true or false. So this question's about DFAs with k states and whether the language of the machine contains a string of length k-1. And that is not true because we can have DFA of any size that has no states that are accepting. And so therefore it doesn't contain a string at all. And so the answer here is correct, that it's false. Statement's not necessarily true, which is a little different than the word false, but it is possible for a DFA with k states to recognize a language that does not contain a string of length k-1. So it doesn't look like it gives any particular example for this, so even though in the exam you just had to answer true and false, you didn't have to give the actual justification for this. But I figure it gets the right answer anyway. So let's look at this one right here. Notice that this one has a bunch of math symbols. I may have to do some things in order for ChatGPT to be able to understand what it's asking. Let's just copy it straight in without actually doing anything modification. It says true, and this one actually is correct also. L is a finite language. L is a concatenation of L with itself. L star is a clean star, which is a set of all strings. So it's just the definition. Intersection is the strings that are in both. Since L is finite, then it is regular, that's true, and the intersection of two regular languages is regular, therefore the whole thing is regular. It's important to note that this statement is only true if L is a finite language. If L is an infinite language, then this thing may not be regular, and that's absolutely the case. So you could find an example of where this is not actually regular, if L is infinite, but it is true if it's finite. Okay, so it gets that one right. Let's try the next one. So true or false. It says it's a regular language, and this one is true. And the way that you do this here is that you find a DFA for L because you know L is regular. And what you do is you take every single transition and you change the symbol on it to be just the letter 1. So the language right here is just a bunch of 1s in every string. And if you accepted a string of length W before, then you accept a string of length 1 of that same length because you convert every single string to 1s. States of the DFA correspond to the possible lengths of strings in L. Okay, so that's not quite true. If you have an infinite language, you'll have strings of arbitrary length, and so you must be able to repeat a state. And so therefore, the states cannot possibly be this. It doesn't have to be the states of the original DFA, but it's generally a good idea to do it that way. If there's a string of length Q and L, there's a transition from Q to Q+1 on the input symbol 1. Okay, so the justification is wrong, but the answer is correct. Start state is the state corresponding to the length 0. So it may not have understood what I said, so what we should try to do is to see if I put the caret symbol in there, would it actually make a real difference? So it looks like it's exactly the same other than the caret addition here. So it's giving the same output. Okay, so we don't need to check this one. Let's try the next one. Language consisting of all strings having an equal number of 0, 1, and 1, 0 occurrences, and L is not regular. So this one should be false because the language L is regular. And so it says false, so the answer is correct here. To show a language is regular, one way is to give a finite automaton for it. For every 0 in the input string, the automaton transitions from the 0, 1 state to the 1, 0 state. Okay, so this will not work because you need to have at least 5 states for this machine, provably. And it says that you can get it for 2 states, a 0, 1 state and a 1, 0 state. It's probably counting some strings as being included that it shouldn't be, or the other way around. Let's try the next one. So the reason I asked this on the test is that the difference of the symbol here in the alphabet actually does make a difference. And so this one should not be regular, and so therefore should be true. This one, the answer is wrong. So note that it says, as in the previous case. I'm not sure if it's referring to this specifically, or it's pulling it from some training data that it was working on. Okay, yeah, the presence of the symbol 2 does not affect the regularity of the language. That is not true. And in fact, I and several others have proven that it is the case that the alphabet does matter for when you want to check an equal number of some substring with another substring. Let's try the next one. So the answer was wrong on that one. Let's try this one. True or false? So non-regular language is closed under complement. So that is true, because if it wasn't closed under complement, that means that if you have a non-regular language, that means that the complement would be regular, assuming that the non-regular language fits this property. Then the complement language would be regular, but regular languages are closed under complement, which means that the complement of the complement is also regular, but that was the original language, which is not regular. And so it says true, so the answer is correct here. Then its complement is also regular. So consider a language L in its complement, and let M be a finite automaton that recognizes L. Okay, so that's not quite right, because you have to assume that it's not regular first. And so M cannot exist under that assumption. So it tells you how to do the complement, okay? However, if L is non-regular, M cannot be constructed, which means that prime cannot be constructed either. Okay, so they did a contrapositive type proof, which is equivalent logically to the original. It's kind of a weird setup in how they did it. So it's like, if this was regular, then you can do this. So let's try this one. This one, very skeptical of whether it can actually get. An infinite set of languages, notice that it says S infinity here. I should probably write this out in English because it wouldn't be able to understand what S actually means here. So the union of the Li is regular. So this one should be false. Wow, the answer and the justification are completely wrong. So it says true, which is wrong, and the union of an infinite set of languages is regular. That is not true, because you can take any language at all, regular or not, and decompose it into individual strings and make each one of those strings a singleton set on its own. Then each one of those individually is regular, but the whole union of all of them is not regular. For seconds right here is completely wrong. For each language we construct a subautomaton that recognizes Li. You can do that for each individual language, but not all of them at the same time, unless you allow for an infinite number of states. It says finite automaton, so that's not possible. So let's try this one right here. Okay, so this says it's not regular. It should be regular because you can have W be a really, really short string, because it says here that the length of W is less than or equal to 1 plus the length of X here. W string can be really, really, really tiny. If you make it the empty string, then that means that X can be anything, because there's no restriction otherwise on X other than it's just a string of zeros and ones. And so therefore, this L language is another way of saying sigma star, every single string. Because W can be set to the empty string and X can be anything. There's no restriction on X whatsoever. The answer is wrong, and it's depending on using the pumping lemma. So let's see if the pumping lemma is right in its usage here. It picks a string 0 to the P, 1, 0 to the P. So it has length 2p, that's wrong, it should be 2p plus 1 because of the 1 in the center. They're using the pumping lemma for context-free languages for some weird reason. Okay, that's fine, I guess. If they prove it's not context-free, so therefore it wouldn't be regular, I guess. Let I be the number of times. If I is 0, then you get the original string. That is not true. If I is 0, you get a shorter string than the original one. That is not actually proven at all. And they're not showing any particular decomposition here, so this is completely wrong. Okay, so let's try the next one. For any given non-empty regular language, let KD be the smallest number of states for a DFA, and Kn be the smallest number of states for NFA. It asks whether or not those two are the same, and of course it isn't, because you can make NFAs way smaller than DFAs. And it says false, so the answer is correct here. Oh god. So this is saying that the language 0 again, 1 again can be recognized by a DFA? No, it can't at all. So therefore, the justification is completely wrong here. It seems to be really flubbing on the theory questions so far, but it seems to do really well on the programming questions. So it may be just on the data that it was trained on, but maybe it just needs to be trained on more theory data. And because there isn't as much of it out there, I don't think. For any non-empty language L star is infinite. That is true. other than whenever you have L being the set which contains the empty string and only that string. And in that case, it's false. So in that one particular case, it is false. So the answer is incorrect here. It's assuming that non-empty probably means it doesn't have the empty string. L is not empty, it contains at least one string. Therefore, this contains the empty string, which is a string of length 0. In addition, L star contains all strings that can be obtained by concatenating one or more strings with L. So if L is not empty, it contains at least one string, so L star contains at least one string of length greater than 0, so that is not true because it's not able to get above length 0 there because there's no other string to attach it to, because the empty string, when you concatenate it with itself, will get back the same result. Okay, so the answer is wrong and the justification is wrong also. For a DFA, the language of the thing is infinite if and only if it accepts some string of length at least a number of states, and that is true because if you have a string of at least the number of states being accepted, that means that there's a loop in there. And so therefore, you can repeat that loop, which has at least one character on it, as many times as you want. And so you can get infinitely many strings that way. It says false, so therefore the answer is incorrect here. For a DFA, let the language be of that thing. It's really thinking that there can be a DFA for that language, and that's not true at all. Okay, so the answer is completely wrong. It apparently is trying to do some kind of drawing code here about making the DFA. Okay, so there's no way that that's any way correct. So let's try an NFA one here. So a computation on an NFA with n characters is a sequence of exactly n plus 1 states, and that is not true because you can have empty string transitions along the way, and that can increase the number of states that you see way more than n plus 1 potentially. And so that is false, so the answer is correct here. Okay, so it's trying to do the same drawing code, which is really, really weird, and it's asserting that an NFA could be made for that non-regular language, which is not true whatsoever. So I'm just going to reload because that is not true. Every NFA is the same language as a GNFA with 2 states, and that is true because you can take any NFA and use the GNFA removal step, the ripping of the states, 1 state at a time, and you will be able to get down to 2 states. But it says false here, so the answer is incorrect. Every NFA can be represented with an arbitrary number of states, but it's not necessarily true that every NFA can have the same language as some GNFA with 2 states. That's completely wrong. It's probably that it's asking whether or not... Yeah, actually I'm not sure what it's really saying. So it's giving like some example here. It's not possible to represent this language using a GNFA with only 2 states because such a GNFA would not have enough transitions to cover all the possible combinations of A's, B's, and C's. That is not true because you can have the transition in the GNFA be a regex, which describes the language of the NFA, and that's what the removal process really does. So the answer is completely wrong here. Okay, so let's try this one, which is about epsilon closure. I'm not sure if it'll be able to pick up what E means. So I'm going to actually write that in, where E of S is the epsilon closure of S. So it says true here, so let's see. So can be an epsilon transition from a state inside to a state outside of the bubble, and that is not true because epsilon closure is defined to be the biggest set of states that you can actually get to from the initial ones just by reading epsilon transitions, reading in that sense. So you just follow all the epsilon transitions as far as you can go. Since you go as far as you can't have a state that goes outside of that bubble when you start from the inside. And so it's trying to do something similar to the example before, and that's completely wrong. So this answer is wrong also. Okay, so it's not looking too good on the true or false here. So true or false, I have a more complicated one here I've done on the channel way back. It's about the number of states in the product construction for DFAs. And so the answer here should be true, but the answer is giving is false, so therefore this is incorrect. F1 plus F2 minus F1 times F2. That is not true at all, because for the union, you are taking every single state of the original one. Okay, so what it's doing here, actually I'm not sure what it's doing. Kind of doing some kind of XOR operation where it takes the ones that are final and the ones that are in both and taking the ones that are both away. But that's not true because for union, you take every state of one and pair it up with every state in the other one. The union is saying this state right here, let's say it's final, is matched up with everything in this other guy. Then that means that you're going to get the number of final states in the first one times the total number of states in the other one, and vice versa. and you will double count the ones that are in both. So that's why there is this F1 times F2 in the middle right here, because you're taking away the ones that are counted in both of them. It's not doing very well on a true-false. Let's try the more complicated ones, or at least I think complicated. Let's look at a pumping lemma proof right here. Notice that I need to potentially add some characters here because it's not able to notice the caret here because it's not in LaTeX. To prove a language is not regular, we can use the pumping lemma. It's probably pulling from some docs that it's found, like the statement of the pumping lemma, which students never needed to do here. So off the bat, it's wrong. So it says consider the string, and it gives an example string of a fixed length. 1, we do not know whether or not this string is of length at least the pumping length for this language. It's saying here that we can pick n equal to 3, because in the language we have n plus 1 first and then n. So it's saying 4 and then 3, so n is 3. But we don't know if the pumping length is 3 or not. We have no clue. And so therefore, this proof is completely wrong. What you would need to do is to say, let p be the pumping length for the language, and I'm going to pick the string same pattern, but with p plus 1 first and then p second. What you do is, no matter how you pump in the first part, according to the rules right here, there's no way that you will be able to stay within the language. You'll be able to pump out of a language. And so it was not able to do that here. It showed that for a particular string, but in order to show it's not regular, you need to show that for every single string that is in the language and of length at least the number of states in the thing, namely the pumping length of the language. So this is completely wrong right here. Okay, so let's try to do this one right here. So notice that it's referencing L1 right here. And so what I'm going to do is put it in the same chat window as the first one, because I had L1 equal to something before. Let's see if it's able to figure out what L2 is depending on the proof for L1. So we can show that it's not closed under complement. So I'm not sure what it means there. So regular languages and non-regular languages individually are closed under complement. So I'm not sure what it is closed, not closed means. Okay, so it made the definition here. Suppose for the sake it is regular, then it's complement, which is also regular. Let L1 be the language defined in the previous question, so it was able to pick it up from before, which is kind of interesting. Consider any string in L1, we can write it as, oh, it's able to do the generic form there, which is really weird. Why didn't it do that before? W has exactly one more occurrence, that means W is in L2, since L1 is a subset of L2, it follows that L1 is a subset of L2. I've never seen that kind of proof before, but the way that you were supposed to do it was to intersect L2 with the language 011 star and 010 star. And what you would get is L1 out as a result. And so the intersection, if L2 was regular, the result would be regular, which would imply L1 is regular, but it's not. So it's really interesting in how it's doing this here. So normally try to avoid subset proofs, because if a language is a subset of another one, unless it's finite or something, you can't imply anything about it. Because sigma star is infinite, it contains every language, and so therefore non-regular languages can be subsets of regular ones and vice versa. So you can't really use that kind of argument here. Let's do this one right here. So this is about constructing deterministic automata. So let's just copy this in. So let L1 be the languages of all strings having at least 1 0, and L2 be all language of all strings where the binary representation is not divisible by 3, construct individual DFAs for them. Too bad I can't actually draw it right here. This DFA has a single state, so that is impossible to do, because you would have to accept the empty string there, at which point that is not in this language. This DFA for D1 is completely wrong. This DFA has 2 states, that's impossible because the language for D2 must have at least 3 states, the DFA for it. And so this is wrong here. Using D1 and D2, give a state diagram for the intersection of the two, constructing the previous question. So I'm assuming that it's able to do this correctly. So I'm not going to worry about this. So I think it had 2 and 2 before. So it's this 2 states and a single state. So it's not really pulling them out correctly, even from the previous chat. So that's pretty interesting. So it's kind of giving some justification right here, but it can't possibly be right. So I'm just going to put the symmetric difference one in here. So there's probably no way that I can get it right here. Describe in English as well as a state diagram how to generate a DFA. It might be able to do the English part, but I'm not sure about the state diagram. I wonder if it's just working off the data that it's already trained on, or if it's actively pulling things from Google searches or something, in case that we ask it something that it's never seen before. But I have no idea, obviously, how this works. I have to see whether or not this affects our teaching in any way. At this point, from what I'm seeing, it's not able to really get to the heart of what the question really is asking. It tries to do some surface level understanding. Maybe it's going to do something in the future, but I'm not too worried at this point. So it says here that the DFA is the same states as D. I'm not sure what D is referring to. Is the intersection of L1 and L2. So it can be done that way, but the final states are different. So the final states are start, start, final, final, where the start and final are the start and final states of D. So I'm not sure that's correct either, because it may be under very specific circumstances, but it's not here. So it pretty much destroyed that entire question. It's completely wrong. So question 4, let's make an NFA for 0, 1, union 2 star. Only the methods described in class. What we did in that particular class was to break the regex definition down into its inductive and base definitions and make a little NFA for each. And what you do is you just combine the pieces as you go. So it's like there's a concatenation here, there's a union here, and there's a star here. And you just apply the inductive steps. I wish I could just do the friggin' diagram here, but instead of having to interpret this code, so I have no idea what any of this is, but it probably will have to do some kind of justification. So this NFA has 3 states, and that might be possible here. No, I'm not completely sure about that. Since I asked about the methods described in class, there's no way that this could infer that kind of info. But let's just try to see what it can do about converting the NFA into a DFA. So we can use the subset construction. And it actually pulled out the regex from before, so that is no surprise to me, but it's still pretty cool to see. Constructing a DFA-D that has a state for each subset of the states of N, so in principle that is correct. It's a better idea to make the states as you go, so you don't have to utilize all possible subsets, because they're exponentially many. And let's see, the subsets are 0, 1, 2, set of all states of N, that's the start state, so that probably should be right, because the original regex had to accept the empty string. Okay, so it kind of crapped out right here, so it wasn't able to get the full justification in. Okay, so let's move on to a new question, which is about this regular grammar. So converting a regular grammar into an equivalent NFA. Come on, ChatGPT. I wanted to get at least one of these questions right. I wish it could just draw the diagram. It's probably going to have another problem on the next question because it's asking to convert the NFA into an equivalent regular expression. I wonder what this regenerate response does. Okay, so it starts in the beginning. Okay, so that's probably not what we want. And I'm going to guess that this one is going to fail for the same reason, because the first one was not able to complete, so this one's going to have a problem also. I'm going to look at the bonus question that I gave. This is about homomorphisms. So it could probably infer that just from the last sentence, because that's a fairly standard proof. But let's see what it's able to do with the whole question. Homomorphism is basically just take a string in the original sigma star set and then convert it to a different string. And the property is that if you have a string in the original, then the homomorphism of that, no matter how you break it up, is the same thing as breaking it up and then applying the homomorphism and then gluing the two pieces together. Let's see, to prove that a regular language is closed on a homomorphism, we need to show that L is a regular language and H is a homomorphism, then H of L is regular. So we have a finite automaton here, so it didn't need to say all of this here. So in general, this will not work. So one of the problems is that H of A is a single string. What you need to do is to have a bunch of states in between Q and Q prime that are each of the characters of H of A all the way across. So it's basically a single transition from one state to another originally, but now you have a long chain of transitions that go to Q prime here. Unless you have the definition of finite automata allow for a whole string in a row. Let's look at the very last question. So a non-regular language and a homomorphism such that the homomorphism is regular. There are a lot of ways to do this because you can convert any string from the original alphabet into the new alphabet in any way that you want, as long as you obey the splitting up part of it. And you can transform a larger alphabet to a smaller one. And so the 0, 1, 2 guy from earlier, you can transform into the 0, 1 version of the language, the one with the equal number of 0, 1s and 1 zeros. And you can transform all the 2s into empty strings, and that will solve the problem right there. One example of a non-regular language is a set of all strings that contain an even number of 1s. Wow, that is completely wrong already. You can easily make a DFA for this because the number of zeros is not important and the number of 1s is just an even number. So that's completely wrong. So it's already regular. And so the homomorphism by the previous question must be regular no matter what. So this is a complete nonsense answer. So hopefully that was interesting. My thoughts on ChatGPT at this point are that we are in the cusp of a new inflection point. And by that I mean way back when computers were becoming a new thing, and computers not the profession but the actual machine itself. These were a revolution because they're going to automate a whole bunch of tasks that we consider repetitive. We're going to put all of these hard workers out of their jobs. At this point, computers are ubiquitous in every possible respect. So where I see something like this going is being able to generate a lot of code and a lot of theorems and proofs. And what we need to be able to do is to verify whether or not the code that this produces or the theorems and the proofs that this produces are actually correct. Because at a first glance, for a student, for example, who may not have paid attention in class and just barely knows what these terms mean, this may seem like a reasonable answer, but they fall flat fairly easily just by a simple rudimentary analysis. So I absolutely see these being used in the future, and I hope that we as a computer science community will use tools like this to our advantage and for public good. So hopefully that was interesting. Leave thoughts about my exam and the ChatGPT answers into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. As always, thanks for watching, and I'll see you next time.